it's time. Almost time anyway.
Almost done?
Yep, I think we have a quorum now.
Okay,
And Julia is set up over here, so we'll have a camera looking at you if you stay.
look at my screen.
Yeah.
Oh, where should I stand? Anywhere?
Yeah, it'd be good to stand.
Stand there?
Just left or just right.
All right.
Good. On this side, right? That's good. Wait.
So, like this?
Yep, that's good. There you are. Yep.
Okay.
All right, a pleasure to introduce Professor Zikmulu of Penn State, who I have known since I was his doctoral opponent.
Before that.
Thesis defense.
Before that.
Well, most notably, right? that moment in history. So thesis defense in the ATH Stockholm system. We did perform admirably, so I'm very pleased. A few years later, when he came to join Questec in his formative years. But then very soon after that was given the faculty position at Penn State University System. He will tell us about many of the things he has pioneered in IC technology.
Thank you, thank you, thank you, Greg. And the first time I met Greg was 1988. And Greg just joined Northwestern, I think, a long time.
Yeah, interesting, yeah.
And he came to ATH, gave a talk on material design.
Yeah.
The rest is history.
You were hooked.
It's so exciting and it's so innovative ideas and present design material. That's really different. So as you have learned a lot from Greg on the CALPHAD and use it, how to use it. Some they talk about CALPHAD modeling, right? And they also talk about thermodynamics. And then see what's the next step or the next steps we can do with this. Okay. We can connect this one first. Okay, now. Last year, didn't do it. All right.
Okay, you got it.
Okay, that's right. So CALPHAD, and this CALPHAD stands for calculation of phase diagrams. And Greg and I just had a paper about the calculations of phase dynamics. Okay, because thermodynamics, right? I think thermodynamics. So this is the CALPHAD logo, as you can see, 1973. That's when it started. As you know, that this is the model of the problem in individual phases. That's the key one. Individual phase, not the system phase. Okay. And then for the phase, you're going to have some variables with the friends of individual phase, the temperature, pressure, composition, and this coincide here. Okay, that's another very important thing about the CALPHAD model, which a lot of times don't learn from the traditional thermodynamics. Then with mobility, that was basically the work of my advisor. And after 30 years, now we think that it is right on side of the small. All right, yeah. And we probably will see how much time we have. And the other properties, you can actually do it. Read about any properties, so it's here. Because if you have a energy, you can capture all properties. Because energy is thermodynamics is the key of everything. You can get thermodynamics, right? You can put anything you want. And interfaces. Okay. So we have a CALPHAD community, it's our website, and we have 3 things we do. We have annual conference. Next month we come here. Celebrated number 50 CALPHAD meeting. And because CALPHAD started here, that's why we share a little text on that too. And then we have a non-profit foundation since 1975. This is the first year at the CALPHAD meeting. We started off with scholarship in 2007 when I had a meeting at the state. And I think it's student scholarship, right? In the chapter here. This is the first time every applicant to that scholarship got award. We can have 58 of students of cover. Have a meeting very interesting that they, as soon as they arrive to the meeting, and if you leave, everything's covered. The food, the hotel, and drinks. Right? Then we have a journal, 97. You can 73, 75, 77. That should be progress. So people starting and find out we should continue to develop it. And the Kaufman was trusting me very much. Actually, I'm not taking boss here. You don't want to get into me, that's nice. And you have our source databases, you probably use Thermocraft, right? That's what this developing in Sweden. I see grad students. The grad students are very important. And we have a commercial database, there's a couple of them. We have open source one, open CALPHAD is actually developed by one developer by Thermocraft. and Kusuma. And we have some chemical from Canada, then Pickup S-Bay is from Michael. Developed by 2 grad students. A Pickup is for 1 grad student, now he's in GPL, and S-Bay developed follow the other one. Now he's at Rhodes Newman. That's the first one. So, you know, as probably Dr. Olsen, Greg Olsen mentioned, you model this one. So it's French of individual phase of the key, and then take 2 types of input data. One is derivative, so energy, from capacity and entropy, activity, and so forth. Another important data is phase equilibrium data. Is when there's no driving force during the process. That's not only no driving force. You see, there's 2 terms here, right? You want this one equal to 0, could be this one equal to 0 or that equal to 0, right? The first one equal to 0, no driving force. That means it's equivalent. Second one equal to 0, then you can talk about it. That's called a freezing in state. But the actually what happens is freezing in state. It's not easy program, but it's called a constrained equilibrium. That was very important in Marcellus. I think that's a very important to by Marcellus, but already done by Larry Kaufman. But Larry Kaufman was not friendly that way. Okay. But here, those guys from MIT is the same boss, like the Greg had. Okay. But when this one started, requirement binary from away and quantum problem, very important. It's extensible. You can do well 78 elements from here. In principle. After this one, as you have done, you can design the equilibrium, the first one. The equilibrium is really kind of a field constraint, right? So that's all equilibrium factor you have is constraint. That's psi equals 0. And they can drive force. If it's in the 3 states, it can drive force. They can diffusion, phase transformation, inflation, and so forth. And even more important has not been explored very much. It's a physical properties. That'd be first and second derivative. So you can have a website, and this is the first book, probably 1970, by Larry Kaufman, first, and it's got a computer calculation on phase time in 1970. That's what I came up with some kind of genome. So it was back in 2008, 2002, the 3rd year, 4th year I was in the Penn State. I need to have a company. You know, I need a consultant to make some money. And people, what name I should use? That's again genome. And the reason we have that name is because, well, so many things, right? Greg's 1988 presentation, and he was my PhD examiner. What happened in the CBC system is that I'm sitting there. Greg was giving talk about my thesis. So I listened to what he's talking about, and he will ask questions. It's really interesting system. All right. So then I said at that time, around the year 2000, the human genome project was a big success, right? So then I said, well, material should be the same. We should material genome. And then the phases in type of genome, which is on the scale. But the individual phases we definitely want to control or try to manipulate. So I said, that's what kind of genome. And as you know, of course, this is a revolution. I was here at Questec. And even before that, Charlie, we have traveled together. There was a big suitcase of laptops. Because not everybody had laptops at that time, so you could not access into the software. So Charlie and I went to big suitcases, like 20 laptops, traveling around the country. And we would go and they set up the laptop and stuff like that. It was fun. All right, so get back to you. And I want to focus on the CALPHAD. The CALPHAD, remember the French company, CALPHAD, right? And that was when Larry Kaufman realized that challenge. He was working on Martin city transformation. He wanted to model iron nickel, right? We know iron is a BCC at Martin side, right? But nickel never be BCC, right? Now he needs to put nickel into BCC, in order to model Martin side. He asked him the question, I need a BCC nickel. The answer is crazy. He says no nickel. Nickel is not BCC, you cannot do it. Okay. So it's not debating at that time. The big name like Ferroelectric against Ferroelectric, you should have to access nickel. Forget about BCC nickel. Okay. But the scientists sometimes stop. Okay. And so he wanted to do BCC nickel. Yeah, there is a lot of less stability, but you need the friendly between FCC. This is he called less stability. That's it. Long state to stable, right? And sometimes you have many things, right? For example, happening no FCC, right? So zirconia has no FCC. So he could have three of all less stability. Great person. He was finding the whole community, basically. All right. And another kind of concise order. Okay. And the very important one is polarization, which I've been working on lately. And also the defects of the side. So it's basically something not controlled from outside. Is internal, it's all coming from light. So it could be huge range of that. So that this CALPHAD method is really extensible, not only for the typical physical body physics forever. It's actually all physical body. That's what I hope this lesson will. But then the question how to get the data, right? So after this one, that was I learned from Greg. I thought maybe I should be different than Greg did, right? The book has 3 rings, right? The chemistry structure property, right? Property. Then I say if I do the same thing, people say it's just Greg, number 2. Yeah, this was different. I said in circles instead of the rings. Okay. So Greg was talking about you have property, performance, you got properties, you got structure, process chemistry, right? I will hit that. And then if you go from inside to outside, you have the thermodynamics, kinetics, which are the defects. Okay. So then I say the left side you must design for the right side for the simulation. But the principle is the same. Basically, going to connect from the what you can measure to what you want to control. And Greg was talking about he had trouble convincing us to support him. Then for this diagram, I said, that sounds good idea. He was the same idea. I Greg gave me his proposals. We checked the proposal by myself. And I looked at it. Fantastic proposal. Why did you found it? 2 diagrams.
You sold it.
That's all it. I think a lot of funding from this and that. And the idea is that when you do some of the kinetics, microstructure or properties, you always talk about univariate phase. Right? You have the FCC, PCC, sigma, love space. You have all the phases. Each of them have properties, right? You have the similarity property, you have the diversity, you have whatever property, elastic properties, dislocation properties, you can extend it all univariate phases. And at the end of the day, we put them together, you talk about the interfaces, right? Okay. But you have to have the property phases first before the interface. So that would be a genius idea, but I thought one to focus on that one. Most of them dynamic, people focus on the whole system. That we afraid of system, right? And that's you know, it's needed to do the face. Of course, that's for the business legal stuff. All right. So that's what the general concept of the face is because of the material. I'm sure there is question this to you already, right? Yeah, 2014. And this only took 2 years for Apple to recruit this lead scientist in December 2012. And 2014 is not only material, it's a product. So that's important, right? So that's very important. So 2 years from the change chemistry to make test the material to make the material to make the product. 2 years. Think about this. Less than 2 years, right? It's the end of 2012. And just show the power of this kind of tool. I'm sure Greg will show this one to you too. I see expired. Okay. And Greg, I just finished a paper. Is that the design of this alloy was based on the work I started at first step, right project to develop a burning resistant material or criteria. Over I spent a very short time, but first they worked on further, and then SpaceX would over to implement. Unfortunately, the explosion last week, but I'm sure next one will be successful. Maybe it's a
It wasn't the alloy.
No, sir, not this alloy. All right. So I do want to mention that all the properties can offer free energy, right? In the free energy, in the thermodynamics, there are two types of parameters. There's one called potential and one called molar quantity. They together called it conjugated variable. Have you heard of that one? P and V are pair, right? They are conjugated variable. TS and mu X. Then you have electric field, electric displacement, magnetic field, magnetic displacement. They're all pairs, right? So one of them called potential. For example, you have temperature, stress, and the stress pressure, electric field, magnetic field, and chemical potential. That's all potentials. Okay. Then that's conjugated variables are the molar quantities. So entropy, strain, volume, electric displacement, magnetic induction, and the moles. Then there's two variables have derivatives and they important ones. For example, heat capacity, okay, and the elastic constant, permittivity, permeability, and some dynamic effect, all the derivatives between the conjugated variables. ES, PE, and so forth, right? But you don't have a B to T, right? What is B to T derivative is? Volume temperature. That'd be this one, right? So expansion. You see, all this physical problem we're talking about actually just linked to the energy. It will be secondary due to energy. And there's one type of problem we don't talk much, is actually the blue ones. So what do you think about the mass, the number of moles of a component to temperature? So that could be positive, negative. So only the red ones are going to be always positive because stability. The off-diagonal ones could be all negative or positive. So experiment could be negative. Have you heard about that one, right? You might know negative sense. So you could have this guy. This one is actually chemical reaction. So for example, your temperature goes up, that component increase, right? So it's chemical A plus B from C. So this is temperature, this is stress, and so this is a chemical reaction controlled by the potentials. Okay? That's good. So this is between the derivatives of the potential and molar quantity. But based on Maxwell relation, they're symmetric. But it is another quantity which has never been discussed in literature. Is a canonical calculus for thermodynamics. I still remember Marcelo said you cannot do that. Let me ask you a question. Can you compare the chemical potential of a component in temperature? Can you say the chemical potential of nitrogen at 500 and 700 degrees? Can you find the difference of this potential? The derivative? I'll give you another example. Can you compare the potential of electrons at two different temperatures? That's a Seebeck coefficient. So a second type of derivative of cosmology is between two potentials. There's all potential. Well, the potential itself is one, right? That's there. But they have another set of very interesting properties. It's some transport, stress transport, electric transport. This is the electromigration, for example. Magnetic migration and cross diffusion. We're very familiar with that. And again, this matrix is symmetric because of Maxwell relation. This equation just shows that you can have the derivative between potential and temperature. So why we cannot do it is because if you skip cell, you cannot do it. You need to change the free energy. I hope that this will become very, very useful. This actually proves that many of the quantities we think are kinetic is actually thermodynamics. As I mentioned, that the Seebeck coefficient is based on the chemical potential of electron as function of the chemical potential. That's the coefficient. Okay. All right. So I want to show you that free energy is not only for material design, it's for materials property design too. Okay. You can capture all kinds of properties, all thermodynamics. Of course, there's some ones are not thermodynamic properties. For example, diffusivity. Is diffusivity a thermodynamic property? It's a kinetic property, right? But thermodynamics is also a thermodynamic property too. Okay. So diffusivity is basically fairly as function of atom displacement. So the barrier, energy at the top and the bottom give you the migration barrier, right? So that's energy. There's any difference at two different positions. Okay. So now the question is, can you capture the energy at that a top point? And that the barrier, top of the barrier, right? Can you capture free energy at that point? Is free energy at that point defined or not? That's another problem because sometimes it's not defined traditionally because it's unstable. If it's unstable, you cannot define entropy, right? And you cannot define entropy. However, turns out the solution for that. We talk about it. I don't think we'll talk about today in class, but that's what we have been working on. Actually, we did some work. So, what's the challenge of CALPHAD? we talk about CALPHAD, you start from pure elements multi-component system, right? So what it means is that you start, this is the paper with one of Greg's former student, Kyrie Campbell, which is not in this. In 2014, we want to formalize this challenge we have. For example, the 6-component system, you start with the pure elements, boundary term, and the quantum rate going up, right? But then the question is that if you change C, for example, you find the problem of C, that the mass stability is not good, you're going to change it. Then everything with big C has to change, right? Okay, you go back, that's huge. Right? That's very difficult to do. Then, you know, I had a student, I said, you know, that's a problem. Students, I'm going to solve it. I like the attitude. With the Richard Otis, each of them, 2012, I said, you know, well, this is a challenge. What do you think? They formulate the problem like this. Basically, when you do that, you start developing molecular data, you develop the data files, you do the integration of the database, they use database, right? So the problem is that after you get database, you got to keep file use it, but then all the information that I have collected are disregarded. There's no way to find it except in that student PC. Yeah. So information, metadata information are lost. You cannot revise it easily. The first problem. The second problem is that you need to not only store the data, but need to software the process of data again, right? So then, as far as the PHP physics, you develop this code, of course. Different code cannot be PHP physics. I have to solve some actual problems. Okay. So then he used Python, which I knew nothing about Python that time because I was doing full C programs, and he came with Python code. Okay, that's fine. So he did Python and actually developed a very nice code. He developed the minimization, including calculation, that's very important. He developed it, and he went to SciPy conference to talk with this Python people to get new knowledge. And it turned out this one, so he took this one after he graduated again. This one actually won a very, very prestigious prize in NASA. So the NASA wide, NASA has many labs, right? So every year, each lab competed internally, get number 1 out of that lab, then go to the whole NASA compete. Okay. So he graduated in 2016, he said, this is a fantastic program, he's going to compete in NASA. So he did. So he first year he did the GPL, get second place, 2018. So then he began get first place, then go to NASA, why did he get second place? Which got it, we sent the check. All right, so the first one. This one is for like some more calculations. You get database, you can GP file, you can load the GP file that does calculations. Most of calculations, some more calculations. It's open source. You can go to CALPHAD.org and you can install it on your computer. And then how about the database, right? So this first step, the database, so then there's Richard started it first, but he graduated as a high enough student. That student joined my group because we saw YouTube of Richard's presentation at a SciPy conference. He said, that's fantastic. He can join us. Then he did this at SPA.org. Basically that now the 2-step of simulate finding. First step is that he only can derivatives of a energy. Okay, single phase individually. So then you value all the parameters. However, you know, you have data, you have parameters, you can do many parameters, right? So you have to have a criteria to decide how many parameters you're going to use. Okay, then you get best performance. So this you have to compromise this too. Because if you get too many parameters with overfitting, very difficult for the prediction and extrapolation. That's the first one. So basically, the first step from the derivatives, then we get a database already. That's the step 1. This is not perfect. That's actually part. The reason it's not very good because the derivatives are not very accurate, right? Okay. Actually, not very accurate. We actually found out the EFI calculations cannot reproduce experiment, and it should not reproduce experiment. If the EFI calculation they do with experiment, the EFI calculation has a problem. Okay, that's actually very interesting. All right. Of course, they have people not agree with me, but I convinced them, most of them now. Okay. And the second one is that because the derivatives are not very accurate, okay, then you have to refine the model, use basically improvement data. So you get parameters more accurate. So you produce temperature like 5 degrees or 0.1%. So we use this Monte Carlo, market chain Monte Carlo method kind of machine learning. And they can derive the primary, also do uncertainty quantification. I can uncertainties of your parameters, your predictions. So another PhD is graduate 2021. All right, so the two tools, you don't need data, right? You need data. So the experimental data is always equivalent. But now you want to do non-equivalent, so with DFT. Okay, that's why second DFT can be many data.
But you can use measured T0 temperatures for low temperature.
Yeah, that's why we estimate. Let's have an estimate data, right? Yeah, estimate and have also intrinsic uncertainty. Right? Okay. So we actually, if you look at this one, this is what a matrix project developer at the MIT, see this group, and then we moved to Berkeley, not him, but the student moved to Berkeley. Then they developed this one. It basically controls workflows, which we got involved with this one. And then, but mostly 0 Kelvin, so we extend to 20 and take it into the each configuration. So that's code again is open source, passing code. And they will do machine learning, okay, because we want DFT calculates a long time, so we do machine learning to do that. And this again for 0 Kelvin is long, one goes of energy. So I got a student, I did previously, graduated from Case Western. Now he started doing some machine learning for us, working with mathematician. We have 2 mathematicians here. We have the machine learning. The models. And then what about the design, right? Remember the inverse design, but most of us will really not do inverse design systematic. We're using our intuition, we do some judgment, then we do simulations, right? You don't really put all the inverse back together. So I was always wondering, can we do that? Okay. Then we had a new faculty 2 years ago, just before pandemic, and he does inverse design. Using machine learning models. So I'm so excited. So I worked together with the proposal. We got a API project. So we got inverse design now. Okay, inverse design is different from it's actually 2 machine learning models come like talk together. Okay, one is from the random property that is linked in the space. That's a very important one. And so this is typical machine learning. Okay, forward. But because this is another process, we talk another machine learning models. When they agree with each other, so to speak, they have a model you can just predict. So what you do is that you can just give what you want, and then we give you the composition. Of course, with machine learning models. Right? Actually, we have a demo now. If you go to, actually, I have a website for a demo I show you later. You can actually now click that one, go to the notebook, binder, in your properties, and give this composition. Give the price, you can also give the question. All right. So input data is important for us, right? And then we have the experiments. That's what I started. I was experiments. Okay, until I came to the United States, I was most of the experiments. Now I'm 100% with simulations. Completely simulations. And as I mentioned, that the experiment analysis is incomplete, is nearly good. And then, like Greg has mentioned, that we can estimate T0, right? For example, that's the estimation data. That's okay. That's but is larger, so it's going to be non-equivalent. T0 is non-equivalent. And the last one is the DFT. Okay, DFT has a major problem. Challenge DFT. That DFT mostly talk about one state. Okay, or maybe another non-one state, 1, 2 state. But if we experiment, you sum all combinations. That's why DFT can never sum all. So how do you solve that problem? That's if you have heard, maybe have not heard about it, we have the theory called the entropy here. Okay, entropy at Z in front of it. That one can solve the problems. It could give you very accurate information, as accurate as the experiment. All right, so I case that, and then last one is machine learning. Machine learning basically is machine learning is that if you take DFT data, machine learning basically shorten time, but still DFT results, right? If you take experiment data, do machine learning, and they basically try to reproduce experiments and use the machine learning model. machine learning does not create new things. So to speak. It's just how to represent this data in the new network. But when the reverse design, they create some new. All right. So for thread one, we create the ocean of data towards the data. I was talking about it in our approach. I asked our staff at Penn State, and she drew this very nice diagram to me. She's like, okay, all the data, given the data repositories, some secret data for industry, then you can use your tool, evaluate them in the sky, a database, then use them, you precipitate look at the data ecosystem, look at ocean of data. Not the data ocean, it's ocean of data, it's the ecosystem. So we generate data first. You can, of course, experiments, right? You can DFT, you can do machine learning, and then you can do data processing and packet SK, and also uncertainty quantification. And then after that, you do your design. Okay, so that's what I have this link here. Okay, if you click this link, see again, C is a conditional generative adversary network. C again, demo, it's R2R as a project. But if you click on one, you launch a chip notebook. You launch the binder. You can predict the big design. And also, because it's one challenge professors is that students did work, they gradually disappear. So how to continue this kind of thing? After Greg was very smart, he from Presec. Okay. And then I decided with my students that because we're not making money, we should make it a nonprofit. So this is the Material Genome Foundation, nonprofit for the year and my students. We want to put all our tools, all those tools we have will be part of the foundation. All right, what's next? How many time do I have? How much time?
No, usually about 20 minutes.
Okay, what's next? Right? That looks good. We like the design, we can see the tools, and you can generate data. What's next, right? What's the next is going back to the cave I showed you. There's derivatives. Okay. So we go forward, have to think backwards, right? Okay. History, and after this 150 years of history of thermodynamics, first by Gibbs. But of course, anything you actually do not know where it started. I can always trace back. Okay, trace back to Rome's time, even before that, right? Okay. But let's start with Gibbs. Why I start with Gibbs? Because Gibbs did the combined law. Before Gibbs, the first law and second law are separate. And he put them together. But actually, he did not put them. He did not really put them together. Okay? But we believe he did. And we show what he did not do. And then the importance, another important thing Greg Gibbs did is a statistical mechanics. Gibbs invented the statistical mechanics by himself. He's a single by himself. And what happened is that Gibbs studied here at university. He heard about this first law, second law. He took a trip to Europe. He traveled around Europe and learned from people and came back to that the combined law. That's fascinating. So that's important. Travel, talk with people. Like Greg traveled to KDH in 1988. Inspired me a lot. And then another important of thermodynamics is quantum mechanics. Here's the quantum not thermodynamics, but no, quantum mechanics is thermodynamics. Why? Because quantum mechanics gives energy. Energy goes into thermodynamics. Of course, quantum mechanics not only give the energy, it starts from electron, right? Electron structure, the integration, the entropy, and so on. But at the end of the result is energy X. But quantum mechanics has been was discovered, but it's not used because it's too complicated. Until 1960s, density functions. Now it becomes useful, quantitative with not everything. And then knowledge equivalent. Now it turned out it's the issues that when Gibbs divided his combined law, he dropped off the knowledge equivalent. Then basically no second law in his combined law. So his combined law is not really combined law. It is the first law and something. So because people know that we still needed the non-equilibrium, so then when you reverse thermodynamics another branch, actually again, many people did that. like the Kelvin, the Thomson, and so forth, but it's on solder systemizing. And then preloading applied to chemical reactions. So it's very true, very, very important application in 1930s and 50s. And it came out, beloved Larry Kaufman, 1950s, he was resting there, not 60s, resting here. He went to mountainside, then he developed CALPHAD method. Okay. CALPHAD method, in my opinion, is the first digitization of thermodynamics. Put it from there in digital. We talk about the fourth industrial revolution, right? Digitization. Actually, that is digitization of thermodynamics, digitization phase step and so forth. And then I mentioned that Masura in his book, he talked about this with internal processes. So you can see that the reverse fraction is too dominant. So then what happened to this one? So I didn't really focus on this for myself, but during my sabbatical 7 years ago, 8 years ago, I went to Australia, part of my sabbatical, and that person does the thermal transport. That's on cycle relations. So then I started being interested. That's why I do sabbatical too to become a professor. And he did sabbatical in Cambridge, right? I did that to that school. So you learn how to use it. So he taught us one day, I said I couldn't understand how can that work, right? So I did it. It took me 6 years to figure out what's wrong with the cycle simulation. So I wrote a paper. I wrote a paper, nobody wanted to publish it because it gets on cycle, it's not good, right? And then one of my friends in the journal, he said, oh, you have to write a long paper. So I had a short paper, Then I extended to 40 pages. Okay, so I did something on that too. All right. So all this you have keys is the intro. Okay, it's intro, it's the key. Let me see if this paper. So the main thing is entropy. What is entropy? Well, I asked question of person thing. I said, and why it's important? Because everything is driven by entropy change, right? And how to measure it? How to measure entropy? If the material, how to measure it? How to obtain the entropy of that material? Anyone has it here? We're not in experiments now. This is measured heat capacity. With the heat capacity method, integration get entropy. But yeah, it's constantly, which is the law, which we can zero is impact. And how to predict it? And as far as I know, except the entropy, no other person can predict the complete total entropy of the system, except the entropy. All right. Okay. I want to learn some Chinese too. Okay. So I don't know how, I haven't found out who invented this word in Chinese, because entropy is a kind of new term, essentially. So this is how you write it in Chinese. That's in the artistic way. If you look at the two words, everybody understand this one? No? Okay, there's two parts, left and right, right? The left side is fire, right side is negotiation. So you negotiate with fire, that's what entropy is about. All right. So where did it come from? It's because first industrial revolution, and people invented a steam engine, right? They want to improve the efficiency. They found they could not improve the efficiency. It stays there. Okay. And have you ever seen this one?
Iron Bridge.
Iron Bridge. The first iron bridge is in Birmingham, next to Birmingham. Okay. Do you know? Oh, they probably do Wayne's Beard. Do you remember Wayne's Beard?
Oh, why was it?
Wayne.
Oh, when? I thought 70.
That's right, because 76 is when the industry revolution started, and it's a 76.9. Still there.
Yeah.
You can still walk through it. Okay? Same steels, same iron, not steel. Well, that's some replacement and repair it, but still same thing. Yeah. So it's because of this kind of thing, because of this the iron we made, then you can use the steam engine. Okay, and then the efficiency problem. Yeah. So the process looking at many people again. And then people find that he defined that S change is equal to dp over T. That's what defined. That means you want to put the steam to produce the work, right? They find it cannot be 100% because some heat is lost. If I lost the heat. So entropy was first part lost by heat. Heat is lost. Okay? And then flash is divided by entropy. They define like dq divided T. Okay. Then you found the second law, any process have to be positive entropy reduction. That means that entropy is lost. Okay. Cannot use it to work. So that was you see, 1922 to 1988. Then came another genius with Boltzmann. Boltzmann said, come on, we should have absolute entropy, right? He said we should have absolute entropy. As you see that I have this deal, he's great, right? And as you can is S equal to log W, right? K is going to constant, W is configuration. And this idea is so innovative, everybody was against it.
What was the role of Carnot? He was in Napoleon's army working on ballistic projectiles and things, and he wrote that book, Motive Power of Fire.
Yeah, that's what he did. He actually came out of this equation, right?
Yeah.
But he did not formulate it entropy before. Yeah. So Clash's formulated this form. And also Clash gives name entropy. I think, yeah, you go back to there to Canada and start. So you see, it's two conflict inside. One differential, one heat, another configuration, right? So this two are not. That's why this two is divided. So what Gibbs did was that let's compare to the air dependency. Okay, they look at this one, right? If you look at this equation, if the T on the other side, it will be dq with TBS, right? That's really what he did. But I have to remember this one means equilibrium. All right, so that's what Gibbs did. He did the combined law, and he said d to dp plus dw. If that was hydraulic work, you have the dp the TDS. That's combined law. But the question is, combined law which does not have second law, right? Because second law is positive, right? The second law doesn't have equal sign. That's why you have to separate together close to very long. But he made the trick. He said, okay, if I talk about equilibrium only, right? And this term disappears, right? And then if I put this equation back in the combined law, you can back in the first law, you can combine them. So that is because good and bad. The good thing is that we can put entropy introduced. The bad thing is that in the whole world, producing thermodynamics with equilibrium. It starts from this equation. So Gibbs tricked the people, think thermodynamics is equilibrium. What is that? He's equilibrium. Then he got this equation. I say, I mean, is comes S and V. So everybody's excited. The person most excited is a guy in England called Maxwell. In the Maxwell relation, right? So Maxwell got his paper, Maxwell, wow, that's fantastic. Because entropy now is in the combined law at the first time. Okay. Then he drew the model, he made two models. He made a model with the US function S and V. He drew the edge surface. And I saw that he made one since we know he said one Gibbs, right? The few years later he passed. He was the first professor at the Cavendish lab, and inaugural professor. And then I went to Cavendish give a talk. Tomorrow this guy didn't call it. No, we'll have another one here. So I actually mentioned it before. So it was fantastic. It's in the Cavendish lab. All right. So entropy change. What about entropy change? So if it's equilibrium, close the equilibrium, the relation from the heat from the sun to the earth is actually the entropy change. But it's measured for heat capacity. But if it's open system, you have each mass has an entropy, right? Okay. If it's not equilibrium, you have entropy reduction. So now what happens is that you still have this equation, you can just solve dq, but now I have two more terms instead of just one term. Okay. And then put this one back in the combined law, the first law. You got this is true combined law now with the TDS, dW, and what the Gibbs had. Now you have the mass. Now you have the entropy reduction, second law. Now I can define this one as chemical potential, which has entropy in chemical potential. That's also very important. Okay. Now, if it's equilibrium, then it goes back to Gibbs equation. If it's irreversible, you have extra term. So the question is CALPHAD. See, now I go back to CALPHAD about the CALPHAD modeling. That's why it's so important. So CALPHAD modeling is for non-equilibrium. That's why it's so powerful. Okay. So because you have to decide it. And then you can do energy, right? Given the condition, you can do all kinds of energy. Now the question is how can we get this in terms? Okay, how to predict it? How to predict it? Again, it goes back to Gibbs. Gibbs another important contribution, as I mentioned at the beginning, many people did not pay attention is the statistical. Okay. This was why you feel from the you can derive this one is the dt derivative is minus, and then if shown is equal to summation of probability of different configurations. And that is so critical, I've read a few times, is that he said a few times, this configuration must have the whole system configuration, not only the particles moving. Many people talk statistical mechanical companies do the things moving in the system. People say they should not do that. And they get a partition, they get a probability of the configurations, they get a partition function. This is standard statistical mechanics, Gibbs derived in 1901, just 2 years before he passed away. And then I visited Cambridge, I visited Stephen Hawking, and I was hoping I could see him there, you know. I didn't know that. And I stayed there for 4 months. My backyard, the house in the back is his house. Yeah. So then he passed away, and the college gave him a plaque out of his office because he was buried in Westminster because the royal family wanted him to bury next to Newton. So he's next to Newton. So now when I saw the situation, I said it's not an issue here because remember I just showed this previous slide. People said that entropy has logarithmic scale, right? Logarithmic. This equation is no logarithmic. So it has the area law they call. The other the was constant, the line of speed of light and so forth. This question no logarithmic. So that made me interesting. So I did that. I have not really come up why this is logarithmic missing. All right, configurations. Basically, I will show you a movie, YouTube, about configurations, right? Because it gives it the PK log PK. So if I show this one. Okay, what do you see? On this YouTube, when at the beginning you see is cage or bird, right? So when that person starts spinning, you see bird cage. When spinning faster, what do you see is bird in the cage. Question to you: which one is correct? Is bird cage separate or bird in the cage correct? In the cage. Sorry, both are correct, right? Why both are correct? But they're different. Right? That's right. So how do you define the way you see? What does that mean, the way you see? How do you quantify that process?
How fast the light travels.
Absolutely. The speed, the resolution, right? The resolution. Okay. So then I give you another one, let titanate. Okay. I sort of have one more slide here. Let me just see. I should have one more slide here somewhere. So if you look at the lead titanate, I think one more slide. So lead titanate. So lead titanate have here is that we know that low temperature tetragonal for polarized, high temperature cubic, non-polarized, right? Okay. So it's very clear. If you X-ray, you find the tetragonal and the polarized and high temperature non-polarized. So now if you do the spin, okay. So what happens is that, let me go back to the last. So if you do a simulation, okay, by the computer, but actually, of course, there's some experiments there too. Okay, this cubic, then there's the white one is cubic. When you look at the inside of each titanium atom, you find it's not cubic. It's always tetragonal, polarized. And if the temperature goes away from the transient temperature, it takes longer time for to change. So what it means is that you actually have, if you do X-ray, you see the tetragonal or cubic, high temperature cubic, low temperature tetragonal. However, if you do EXAFT experiments, there's a high resolution, you see all tetragonal. So cubic is correct, tetragonal is correct. Okay, it's a resolution issue. You do computer simulation, you can look at each atom, it's all tetragonal. Okay, but of course, when the triagonal switch at the middle point is cubic, right? So you can still some cubic, but overall could be either tetragonal or cubic. It depends on how fast they change. Okay, that means you need the configuration. If you do the configuration, turn out the polarization like this or like that. It's only turned out only 3 kind of configurations. Is a Ferroelectric one with polarization. You have 90-degree domain one when it goes like this. So 1 goes second, 1 goes second, 90 degrees. If 1 goes up, 1 goes down, you get 180 degrees. Turns out very simple, only 3 of them. Then you can take all 3, you can calculate the energy with DFT, and then put them back, and you can predict transition. That what does it mean? That means you cannot predict the energy very accurately. And it can calculate it. And there are many things we can do with it. Okay, I'm going to stop here. But 3 more slides is that now that means the entropy from Gibbs only cover one configuration, one level, one scale. But if each configuration has an entropy itself, you have to add them back. If you add them back, you can all the way down go to electron level, as quantum mechanics give us. And then so you have top down, you have bottom up, then you get an entropy in the middle. Basically, we have to say because this one is from top down, this one is from quantum mechanics, the bottom up. They put them together, you get a full total entropy of the system. Then you can calculate it from DFT for the first part, and then put it back together with the statistical mechanics, we can entropy, they can do it with the experiment. So then for the lesson we learned is that DFT alone or the statistics alone is not enough. You have to put them together, then you got a total entropy of the system. Then you can get the friends correct, then you can get the all kind of predictions. So we have done magnetic, we have done ferroelectric. The next one I'm doing, it's actually very close. It's actually EK to FK, the concept of energy. We are working on a number of systems. The latest one we're working on is to use this one to predict the superconductors. I just got funding with that. Okay, so that's the future in my research. Predict the entropy accurately, predict the phase accurately, then CALPHAD modeling will not need a phase equilibrium. Directly from the derivatives of the or French itself.
All right.
All right, thank you very much.
Oh, then we found the unified field theory that Einstein was looking for. Very good.
Well, so we just really
About
want
that? Anything else you need to know?
we want to go a step further. This one is that use this one we demonstrated on sideways. Science equation is theoretical, not fundamental, and turn out it's accurate. All right.
Okay, we heard it all here. You were there.
Are we good? All right, welcome.
Okay. All right, it's your show time tomorrow. Okay.